always at normal, perpendicular to the surface, and inward. So now the surface is inclined. How would that pressure prism be translated to this diagram? You know the base is still OGH, and it has to be normal to the surface, normal. And inward, towards the surface. Right, what is the base of this pressure? Well, we just said, it's going to be OGH. What is the pressure at the surface of the water? 0. All we did is take that pressure prism and rotate it. Rotate it by angle theta. Same pressure distribution due to the height h have not changed, but with that geometric change, I have now my average pressure, still the same. And someone tell me what that average pressure is for this new diagram? This may not be transparent. I haven't changed my geometric centroid. It's still half the depth from the free surface, even though the surface is rotated. At the centroid, I'm still 1/2 the distance from the free surface. So with that, what do you think is the average pressure? OGH over 2, just like before. Let me stop. This is not something transparent. This is the simplest building block approach that I can relate to this problem. Do you agree? Can anyone have a question? Please raise your hand. Yes?
We're going to do area next, I guess.
That's exactly what I want to do next, but one step at a time. Yeah, that is exactly what we're going to do
You
next.
just have force equals pressure, and I was like,
No. I'm sorry. What have changed now is the area. It get bigger now, because before it was just capital H times 1. Now that vector surface is considerably bigger. Well, how much bigger? From trigonometry, is h divided by cosine theta. Why? Because you look at this triangle. Right? It's a right angle triangle. The vector surface at an angle is the hypotenuse, and the projected area is this h divided by cosine theta times the unity into 1 into the paper. Yes?
Can you explain that expression?
I'm sorry?
Can you
Oh,
explain that?
okay. So the average pressure, if I would draw the previous diagram down below, where the surface is vertical, the average pressure, which is dictated by the height, and the height only, have not changed. That's what happened. Only the surface had inclined. But the height h is what dictate, small h is what dictate the pressure and nothing else. Right? Good question. Location. Well, we're going to do the example to help find out how we deal with the location. Turns out when the angle get changed from 90 to a theta, we'll have to deal with the location differently, and it's best illustrated by the example in class, which is very, very similar to your homework. So what are we tackling? So this is a very academic problem, but it helps illustrate all the concept we talk about. I have a inclined plate that hold water on the right side for equilibrium. I have a 10,000 pound force held by a pulley hinged at the top of this gate, which is 15 feet. This is not per unit depth. You're given the dimension into the board, which is 10 feet, into the paper. And this is water. Density is given. And for simplicity, forget the weight of the gate. It's negligible. Small enough. What I want to find out from this diagram is at what height h, that the gate will start to tip over counterclockwise. That is, the water will start to escape with the gate falling down. Do you understand the problem statement? Any question? What's the key physics involved in this problem that if you write down that equation, I have to give you half the credit for the problem with no choice? What's the most important equation of static equilibrium you will apply to answer this question? Sum of moment. Very good. Sum of moment. That's all I want to do. Right. The physics involved is asking summation m in sum of moment at the point B, at the hinge. This is a hinge. So that the gate is free to rotate. And that is the physics. That's what I meant by the physics of the problem. So using our superposition principle, I'm going to take the gate, and for one more time, I'm going to draw the 14.7 distribution on the dry side, like we did before. This is PA. What is the ambient pressure on the other side of the gate? We did that before. This is the same question that I have hopefully clarified already. If you draw this 14.7 on the right side, what will it act from where to where? From where to where? Only on the west side? Only on the water side? No. Top to bottom. Always. So that it has no net contribution to the gauge whatsoever. Yes?
If you had two different shapes, like let's say you had a flat surface over here, and like a curved surface,
Like a dam?
it would still cancel.
Yes. It's not easy to visualize, but the answer is yes. The curved surface is a little bit more complex geometrically, but the answer to the question is if you resolve the velocity, if you resolve that pressure into the horizontal component, you will convince the cell they all cancel. Okay? So fair question. Other questions? So what left is then due to the water side of height h, and based on the inclined dam problem that we have done, this will be rho gh at the bottom, superimposed on 14.7, and a rotated pressure prism. As such, and the forces due to pressure again is always normal or perpendicular and inward towards the surface. So translation, what I need to do from here is now find for a free body diagram of the dam, like you see in static, forces due to the 10,000 pound, and a mean to calculate that reaction force due to the wet side, the net force to be determined, and the location. Once I have that, problem is done. And that's what we'll do in the next 5 minutes. Do you see that? Do you understand the physics? Any questions so far? Any questions so far? Is it more complicated because of the rotative surface? Okay? Net force. Average pressure. Using the diagram on the right-hand side, try to relate to that. Can someone tell me what the average pressure is? Using the diagram on the left. So rho G times what? H over 2. Very good. Nothing to do with the rotation. H over 2. No more, no less. The area now is the inclined surface which we have to deal with. All right, questions of this average pressure despite the rotation of the surface? So let's march that through. Rho as given. G, 32.7 feet per second squared. H divided by 2 is my average pressure. Now come the area. It's a little bit more complex. But again, with the diagram on the left, can someone dictate to me what that area is? It's something times something. 10 feet